Hello, class. Today we'll be looking at covalent structures. In our last class, we treated how covalent bonds are formed by the sharing of electrons between two or more atoms, bringing their lone electrons to pair up to form a bond known as covalent bond. We also delve into looking at the properties of this bond. There we understood that the covalent bond itself is a strong bond, but the intermolecular bond between the molecules of these covalent compounds are weak. And that is the reason why molecular compounds have low melting and boiling point. Today we'll be looking at how to illustrate some of these structures, these covalent structures, okay, with diagrams. And the best tool to use is the Lewis structure. The Lewis dot structure is the easiest to use. We'll start with hydrogen. Okay, so hydrogen is diatomic. So today you will know why hydrogen is regarded as diatomic. Remember, for compounds, molecules to be stable, they must have a complete outer shell electrons. Okay, and that is the reason why bonding even occurs in the first place. So hydrogen, as you all know, has one outer electron, just one outer electron. And you know, for the first energy level, the maximum electrons we have is 2. So for us to complete that shell, we need another atom, okay, that also have one outer electrons, which is another hydrogen atom, to give us 2, making the first energy level completely paired. So the dotted one here belongs to this hydrogen. The light one here belongs to this hydrogen. That way, we have a complete orbit. Okay, that means my K shell, which is the first energy level, is now equals to, which is the maximum number of electrons expected to fill this energy level. Okay, now let's move a bit further to consider compounds like H, four, and carbon. So this is methane. You know, let's count all the atoms we have here. If you count all the atoms we have here, we have 5 atoms altogether. Carbon has 1 atom, hydrogen has 4. Since carbon has the least number of atoms, carbon will be regarded as the central atom. That is one rule you need to take note of. Okay, and then you spread your hydrogen. So how many hydrogen do we have? 4. So that means if I am distributing the electrons in the outer shell of carbon, I must consider giving space for 4 hydrogen atoms to come in. Okay, carbon has atomic number of 6, which denotes that it has 6 electrons. Of course, K shell takes maximum of 2, that is the first energy level. And L, which is the second energy level, takes maximum of 8. So the remaining 4 comes here. Carbon has 6 electrons. That can be verified from your periodic table. Okay, so now we have 4 outer electrons to distribute. So that means carbon will give just 1 space for hydrogen here, 1 for hydrogen here. one for hydrogen here and the other for hydrogen here. And you know, hydrogen has just one electron. So place one hydrogen here. Okay, to pair up with the one that carbon has provided for sharing here. And then another hydrogen here. You see? And then another hydrogen here. This way. That way, it will keep space very much together. Okay, so carbon, we have one here. Hydrogen has one here. Hydrogen has another one here. Hydrogen has another one here. Okay, so with this now, you would notice something. Okay, the carbon has reached its maximum state here. Look at the L shell, which is just 4 before. Now has 8, which is the maximum it needs to get to. 1, 2, 3, 4, 5, 6, 7, 8 on carbon atom. Okay, and the hydrogen also has 2, because when they share, the 2 shared electron, none of them can lay claim completely to them. Okay, so both of them can lay claim to, because it's bonding now. Okay, so it simply means hydrogen now has K shell occupying 2 electrons instead of 1 electron. And carbon now has L electron occupying 8 electrons instead of 4 electrons. So that way, carbon has achieved stability, okay? And the hydrogen too has achieved stability. If you look at the note on the left-hand side, you will see that of nitrogen, you see that of oxygen, you see that of fluorine, and you see that of chlorine. You can try out some of these on your own, okay, and that will explain very well why we have so many diatomic atoms, okay, in existence. Another structure that I'm going to be talking about will be the line and dot structure. Okay, it's not that different from what we just did. Okay, it's not that different from what we just did. Now, what the line and the line structure actually talks about is basically when you have 2 shared electrons, that is one from each atom, it makes a line. So instead of just showing them as 2 dots, 2 different dots from 2 different atoms, all you need to just represent with a line, and that's good. It has ease of representation, okay? It gives you this ease of representation, but does not really give some certain informations like how much electrons you have in the outer shell of each of these atoms. Now, you wouldn't be able to tell, okay, with the line structure. Okay, so, and it can't really help to determine the shape of a particular molecule. Okay, but with this dot structure, we can easily tell when valence shell electron pair repulsion can be applicable. Okay, where the shape of a molecule is determined by repulsion, okay, that exists by lone pair of electrons on the central atom. Okay, but we can't do that with a line diagram. However, it's good we learn about the line diagram because it's easier to draw and easier to represent. So all you need to do for a line diagram is where you have your 2 electrons, you just draw a line. So the line diagram for methane here will simply be C. We have 2 here, so I'll just draw a line. H, Okay, we have another pair of electrons here, so that will be H. We have another pair of electrons here, that will be H. We have another pair of electrons, that will be H. Okay, so the advantage this has is also that it gives you the kind of bond that exists. It's a double bond, triple bond, single bond that exists between the molecule or the atoms in the molecule. Let's look at where that is applicable. Let's look at carbon dioxide. Okay, if you look at carbon dioxide, the carbon has just one atom, while the oxygen has two atoms. So the carbon, which has a list, to be the central, and then you arrange your oxygen atom such that it will be on this opposite side like this. Of course, we can't have up and down. We just have two oxygen atoms to distribute. So you just arrange them this way. And since your oxygen atoms are on the left and on the right, you ensure your 4 electrons. Remember, carbon has just 4 outer electrons. You ensure your 4 electrons are on the sides where you have your oxygen. So I'll place one here and one here. It has 4, so another one here and one here. Okay. Oxygen, on the other hand, check your periodic table, has 8 electrons in total. So by the time the inner shell takes 2, what will be left for the L shell will be 6. Okay, so that means each of these oxygen atoms has 6 outer electrons. So what we're going to do is we have to make provision like this. Place 2 facing this 2 carbon so that they can pair. Do you understand? And then we place 2 again here so that they can pair with the one provided by the carbon. And then the rest 4, because we have 1, 2, it's supposed to be 6, so you can just put 2 here, 2 here, making 6 all together. And then I can also place 2 here and 2 here, making 6 all together. Okay, so it means I've represented everything together. And the reason why I have to place these 2 facing this carbon is so that they can bond together. Okay, that way, if I want to count after sharing, if I want to count the total number of electrons that oxygen has, remember L is 6, L is supposed to be 8. That's the maximum for that energy level. So these 2 from carbon will make it 8. 1, 2, 3, 4, 5, 6, 7, and 8. Same thing applies here. 1, 2, 3, 4, 5, 6, 7, and 8. So that makes oxygen stable now. And carbon also has become stable because when you count from here, 1, 2, 3, 4, 5, 6, 7, 8. Carbon 2 is now stable. Okay, so if I want to draw the line structure of this compound, all I need to do is, remember, anywhere they pair up is a line. So I have a pair up here, you will agree with me, 1 here, 1 here, and there's a pairing here between carbon and oxygen, and there's another one here. So that makes my carbon dioxide to have double bonds on both sides. So you can see what a line structure, information in line structure can also provide. So it tells you there's multiple bonds in carbon dioxide, which are double bonds. Okay, you can try that of nitrogen. You will discover that you get triple bond. Okay, when you get triple bond, it means you're correct. But if you don't have it, you can play the video once again. you understand better. So please don't forget. Thank you for watching, and don't forget to click on the subscribe button so that you can have access to new videos that will be dropping on this channel.